Right. We've been very privileged in the last few years in the cosmochemistry community to be able to study material from two carbonaceous chondrite-related asteroids, Bennu and Ryugu. So today it is a great pleasure to welcome to you this fifth Ed Scott lecture that will be given by Dr. Motoo Ito, a principal researcher at the Japan Agency for Marine Earth Science and Technology, otherwise known as JAMSTEC. Motoo will be talking about the key discoveries made from the study of material returned by the JAXA Hayabusa2 mission to asteroid Ryugu. Motoo is a leading expert in the analysis of extraterrestrial materials using SIMS nanosims techniques. He was team leader of the phase 2 Kochi team studying Hayabusa2 particles after their return to Earth in December 2020. I was one of the team members participating and had the privilege of working closely with Motoo on this amazing project. He did an outstanding job in organizing and focusing the team, and it was certainly a major highlight of my professional career and also a lot of fun, I should add. Motoo got his master's and PhD from Gakushin University. He's worked as a postdoc at the University of Arizona and a research scientist both at the Johnson Space Center and the LPI. And so it's a great pleasure that I asked Motoo to present this fifth Ed Scott lecture. If you want to take it away, Motoo, thank you very much.
Okay. Sure. Is it okay to speak?
Yeah, no, you carry on.
Okay.
Yeah.
Thank you very much. Okay, so this is Motoo Ito. Thank you very much for the introduction. First of all, I would say I was so shocked past week. It happened at the Los Angeles area, the wildfire, devastating wildfire. I'm very sorry about that. So if we, Japanese community, can do anything, please let us know, okay? And also, great pleasure to give a talk today. This offered from Ian Saunders and Richard Greenworth. So today, I would like to share my screen. How do I do that? Okay. Pointer. Is everything okay?
Yeah, it looks great.
Looks great.
Yeah.
Okay, so today I'm going to talk about exploring Ryugu, key discoveries from Hayabusa2 asteroid samples. Okay, briefly introduction about the JAXA Hayabusa2 asteroid exploration. Okay, so about 10 years ago, December, it was launched. And then 2018 June, the Hayabusa2 spacecraft was arrived at asteroid Ryugu. Then took a beautiful picture of the asteroid and also the surface of the asteroid. In 2019, February, July, the Hayabusa2 spacecraft conducted two sample collection from two different locations. I still do remember 2019 July. It happened during the METSOC meeting in Sapporo, Hokkaido University. Okay, so we have about approximately 5.4. Wait. Excuse me. We have now approximately 5.4 grams of highly altered materials, and it was abundant organics and hydrated silicates. It is, of course, very pristine materials without any terrestrial alterations, which is really good for our sample analyst. So here in more details, 2020, December 6 to 7, the sample container we recovered at the Australia Umira Desert. Then after just 1 week from this recovery operation, the JAXA curation people will open the sample container we found this very beautiful black dirt from the asteroid Ryugu. And here is just 1 minute video on during the sample container opening operations. So please have a look. I'm sorry, this is in Japanese, but you can enjoy. So I was so lucky because I watched this video on time. So I was so shocked. First time I saw this very black and big grains in the container. So then we start thinking about how do we analyze these pristine samples with our instrumentations and also with our team. Of course, I am pretty interested in not only the isotopes, but also organics material. It's done. Okay. Okay. So I think 2021, end of March, we visited to JAXA Curation to take a closer look at the Ryugu sample itself in the JAXA Curation facility. Then we started more thinking about how do we measure sample and what kind of material we should compare with based on our current knowledge about any extraterrestrial samples, including meteorite and IDPs and return samples, especially from comet. And here that was, I think it was June, we received a sample from Dr. Tsuda and Dr. Usui. This is myself, Shogo, and Iso Nakamura here. This is a kind of a ceremony, but this is just a starting point for the first year analytical campaign. This guy is our largest sample. The sample size is about 4 millimeter by 3 millimeter. This was really huge. It was difficult to handle not only the sample preparation, but also how do we prepare the samples itself. This is just before we start analyzing a CAT scan at the spring 8. I still remember this kind of atmosphere, and I was so excited about that. Okay, so all samples were conducted, including sample handling and opening the sample container in the nitrogen-filled globe box like this. So here, I will the kind of scene we prepare the sample, and this is a scene of the first look by the synchrotron CAT scan at the spring wave. This is Masayuki Uesigi, by the way. And here, after 15 or 20 minutes CAT scan of the sample, then we start discussing about what kind of mineral and material fracture and anything in the sample. This is Makoto Kimura, Masayuki, and myself and Usui here. Okay, Ryugu asteroid science is pretty simple. This is a key to understand the origin and nature of the solar system, as well as the asteroid meteorite collection, correlations, and the water rock interactions, and evolution of organics on the small ALS bodies. Here is a very simple questions when I thought about the Ryugu samples. What is that? Compared to current knowledge of meteorite return samples, like Hayabusa, the Hayabusa Ito samples and IDPs, and also cometary samples. Made of what? The hydrous, anhydrous minerals, organics. Of course, there is a soluble and insoluble, and pre-solar grains. The abundance of this, and also three-dimensional structure are pretty important. So here, the when, where, and how did this form? So basically, we have to understand mineralogical textures, chemical composition, including major and trace element, and the crystallography, and the stable, and the radionic isotopes. So here, more details purposes of our team. The first one is the organics and their relationship to the associated minerals. Especially, we are interested in phyllosilicate, aqueous activity on the C-type asteroid, Ryugu, and the chemical or physical conditions in the asteroid planetary symbols in the early solar system. And finally, what is the starting materials of the solar system? These four fundamental questions can be solved by the integrated analysis of return samples. However, we have to think about these topics, analytical approaches and tools for safe sample safety involved to maximize the science gain from limited amount of the material. Because we have, we have 5 grams, but the first analysis, first analytic campaign we received for the team is only 100 milligrams. So requirement for the sample safety is safe transportation, not only the nationwide, but also worldwide worldwide. And also, more importantly, the instrumentations, for example, TM, NanoSIM, StickSIM, and so on. And transfer vessels for any instrument minimize terrestrial alteration and contaminations. Our team is focused on the development of these two items. The analytical strategy we have to think about it is the micrometer to millimeter size of grains. So first, when we start thinking about the procedure for the analysis, the sample should be micrometer size. But in reality, we have 4 millimeter samples. Should be different in terms of sample preparation. What is the purpose of the planetary science, scientific purposes? And this is a pretty much a pristine and uncontaminated materials. We have to be sure this procedure should not be any contaminated materials inside of the sample. Organic matter, SOM, and IOM, subject to a range of techniques. We have to think about it. Okay, so best analytical result from return samples. Of course, as I say, the transportation nationwide and the international facilities, and they use several types of instrumentations. The transfer process causes severe problems. For example, previously on the Ito analysis, SEM first, and the CAT scan, the SEM. So it was obviously the sample was broken. We don't like this kind of stuff. And we have to develop a universal sample holder, TM made by gel, the NanoSIMs or SIMs made by Kamika. So these are different sample holders. We have to work on this. And transportation container, for example, JAXA to Springate. The distance is about 800 kilos. How do I do that? So here we work with JAXA curation people. Develop the devices. Here, FFTC and analytical result on contaminants, especially small carry-on impactor, fed back to the JAXA curation. We published several papers about that. And here, the development of integrated bulk and microanalytical techniques. This is also, we published several papers about this. For Ryugu sample, especially not only for the FFTC, this is only for the transportation of this size. People may know about this, but also individual sample cases like this. This is 1 centimeter, I think this is a 2 centimeter in size. So after we recognize the sample is huge, like a 4 millimeter, this is not enough. So we quickly, JAXA people quickly developed the Sapphire case, the larger Sapphire case for the larger samples. So this is the individual case stuff. And here, universal sample holder, especially for the stick SEM analysis. So here, the universal sample holders for microanalytical instruments of FIB, TM, nanosims, and 6M for the coordinated analysis. So this is a kind of our basic concept. FIB is a central instrumentation for these TM, 6M, nanosims analysis. We developed two different sample holder. The one is for we call the Koch grid. This fit to the JO type. And the others is Koch clamp. So this fit to any FEI or Hitachi TM instrumentations. And these two grid can be fit to the nanosims and also stick SEM both. Of course, people here, the similar concept research platform have been reported from these two papers. And also we avoid the terrestrial contaminations and any alteration by the terrestrial atmosphere. We developed the transfer vessel of the nanosims, all done in the glow box here. So this is a FIB grid, and we prepare the sample in the globes like that. And finally, this is a sealed sample holder or dedicated to the nanosims, and the sample goes into the nanosims. However, it's not enough. We have to think about the proper order of the analysis to avoid alteration of chemical information like light element isotopes and organics and texture. Here, for example, TM, we got this kind of information. But after the TM irradiation of the sample to the sample, so this affect hydrogen isotopes, organics, and weak minerals. And the SEM as well, and synchrotron radiation, especially the organics. And the stick SEM pose another problem. I will talk about that later. So organics, especially for the aliphatic peaks. And nanosims is invasive analysis. So probably we can get isotopes elemental distribution with a very high spatial resolution. But organics will be destroyed. So which one in microanalysis should be conducted first? We have to think about it. So this is a way of the analytical analysis. The CAT scan first, then FIB, the sample preparation, and the stick SEM, nanosims, finally TM. With those proper sample handling and FIB preparation here. Okay, another thing is transportation of Ryugu samples and the COVID-19. We do remember a few years ago, we had a very severe problem, not only especially for the people interaction, not only the nationwide, but also internationally. So we asked the help to proper organizations and the personnel, including the government. Here, we have to send a sample to UK and the United States. First, we contacted the UK Embassy of Tokyo, and they discuss about any configuration to deliver the samples. They deliver sample from NIPR to UK Embassy, like this. And then finally, Ryugu samples arrived at the Open University in 2 weeks. Richard got a sample at the time. Okay, so the US is more complicated. I have to contact to the Consulate General of Japan in San Francisco and discuss about the possibility for help to the next. with this guy's help. Then we prepared every documentations for regulation for the safe delivery to the United States with MEXT and MOFA, NASA attaché of US Embassy, and the US Embassy in Tokyo, and the ANA in 2 weeks. Then the Ryugu samples to Consulate General of Japan in San Francisco, then UCLA. This happens only in 2 weeks. So again, thanks to this help, the sample were delivered to the 2 countries on time. Okay, I think we are pretty much ready for the first analytic campaign of our team. Here, initial workflow. So we start non-destructive techniques, followed by the invasive analysis like SIMS and nanosims, and then destructive techniques. JAXA accuracy people choose 8 samples, 4 from chamber A, 4 from chamber C. Then we already have some very basic data obtained by macro omega at JAXA accuracy. And then we conduct a quick high-resolution CAT scan at spring rate. Then which one should go to the micro analysis or bulk analysis? In case of C68, so this is a red line is a flow of C68. Like here for samples chipping at the spring rate in the glow box, there's some leftovers here, not exposed to the X-ray. This guy goes to FIB and the 6M nanosims GM. Other fragment goes to laser fluorination or neutron activation. And here other goes to the more bulk analysis, mineralogical texture and the in situ analysis, starting from optical microscope. And I don't think we did Raman, FECM, microprobe, and SIMS at the UCLA. And here, 4 millimeter size Ryugu sample. This is an optical image like that. And this is a CAT scan image on spring 8. After we take this image, we prepare this particular cover for each samples and where should we cut of the sample in the glow box, like this. Okay, so first discovery report of the Ryugu sample analysis. So there are 2 main articles from Science and Nature Astronomy. The initial analysis team, 6 papers, is Yokoyama, Tomoki Nakamura, Noguchi, Okazaki, Naraoka, and Yabuta. And the curations, we are with the curation teams, the Eizo Nakamura team, and our team. So far, only after 2 years to start a first analytical campaign, I think we have over 200 articles. All are very good, of course. So today, I selected key discoveries of Ryugu sample analysis. Of course, I may miss many important articles, but this time I choose 6. CI chondrite stuff, like a new solar system reference, the evidence of outer solar system origin, and the complex organics in Princeton sample, and the manganese chromium H, and the magnesium phosphate in Ryugu. And finally, this is a more curation activity, is a terrestrial alteration during the storage of the sample. Here first, I would like to talk about the CI chondrite. Ryugu would be a new solar system reference. Here, comparison between chamber A and C. This is the A37 sample. This is a C68 sample. Looks similar, but difference is amount of carbonate and magnetite. if we take a closer look at the A sample on the C68, it's pretty much the same, but some difference. But here, C68, if you take a look at this texture, large coarse grain saponite serpentine phyllosilicate, but also these small particles of the phyllosilicate. So later I will discuss about this, but a lot of organic organics found in this serpentine saponite larger grains of the phyllosilicates. Okay, if we these all samples is a phyllosilicate dominantly in the phyllosilicate, about 60% to 90%. These are very consistent with other literatures like Yokoyama et al. And Eizo Nakamura. And also Tomoki Nakamura's paper is pretty much the same. And this data set is very similar to the Tomeoka and Busek and Moloch et al. This should be a CI chondrite. Very similarity. Here, barococyan oxygen isotopes. So this is the first report in our paper in Nature Astronomy. So this is the capital delta and the capital delta 18. So here these data came from CM literature. And these are CY chondrite and Turkish lake and the bells. The shear organs around here. And the blue point is the Ryugu particle, C14 number 4. So obviously, Ryugu is not CY and CM, but CI. So first time we saw this picture, oh, Ryugu should be a CI or some similarity. And here, this is the capital delta 17 and the big delta, capital delta 17 and the delta 18. So this is published in the Greenwood et al. In Nature Astronomy. So Ryugu around here, the CI around here, some overlap, of course, but different from CY. And this is Ryugu as a studies like this. If we compare to Yokoyama et al. And Eizo Nakamura and Pang et al. Recently published, there are some variations in terms of oxygen isotopic composition. This is most likely a different, how do I say, aqueous alteration activity. Here is I show bulk elemental abundances measured by neutron activation. So here green area is a range of CI. So A sample and C sample is pretty much the same range of the CI. But some difference in the titanium, calcium, magnesium, gold. The gold is this gold is depending on the water aqueous range level of aqueous alteration, and the calcium, manganese is a difference in terms of abundance of carbonate. If we compare with Yokoyama et al. And Eizo Nakamura ICP-MS TIMS dataset, all are pretty much the same, but calcium and manganese. As I say, this is different. This difference is obviously caused by the abundance of the carbonate. Here, the second one and third one, evidence of outer solar system origin and the complex organics in the Pleistocene samples. Okay, handling of Ryugu sample starting from FIV, and then stick SEM and the nanosems. So this is a kind of strategy for our microanalysis of the Ryugu sample. Here, this is the first analysis of this kind of strategy of the sample. So we found the we did a stick SEM carbon nexus image like this. So here, G1 is a nanoglobule, most likely nanoglobule. So this is a stick SEM carbon functional code. The nanoglobule shows a huge aromatic peaks, but almost no other peaks. So after we took a 6M image, we did analysis of imaging carbon, nitrogen, and hydrogen of the particular area. The bulk is more likely this size, but the presolar grain is much abundant in terms of carbon 13, but less nitrogen 15. The G1 is related nanoglobule. This is more likely, I would say no more. But after we took a 6M followed by the nanosims, we conducted TM analysis like this. Of course, they're a very bad shape because of the irradiation of ion image, but still we are able to see many nanoglobules around here, and also presolar graphite. Then finally, we found this was a presolar graphite because due to the high resolution TM image and and also the crystallographic information of the sample. Here, this is our finding, most interesting finding in the Ryugu sample. So aliphatic carbon-rich organics associated with coarse-grained phyllosilicates. So there are 3 different characteristics of Ryugu. So we call the red and green and blue. So green area is dominantly aliphatic carbon, like this. Almost no aromatics, aliphatic here and no aromatic here. But others are rich in aromatic, and both green area, blue area is both aromatic, aliphatic rich organics. First time we saw this is kind of different from the previously reported IOM in CM contract. Of course, 6M can do imaging like this. So red area corresponding aromatic rich organics corresponding to the nanoglobule, I guess. And the blue area is more likely fine-grained phyllosilicate. But green area, if we take a closer look by TM, the shape of this phyllosilicate is pretty much the same of the green area, which is aliphatic rich organics component. So aliphatic carbon-rich organics, they compose at the temperature about 30 degrees. So thus Ryugu has not been heated above this temperature. This is one of our conclusions. And this particular number is a good agreement with initial temperatures, which derived from the carbonate OIS of studies between 0 to 47 centigrade. If we compare with other studies, including Ryugu sample, here this is a which one? This is Murchison, Ogai, diffuse OM. It is obviously we are able to see aliphatic rich component in the sample. And here, we have a cometary dust particle obtained by Stardust mission. So Stardust cometary sample shows aliphatic carbon likely contribute to spectral intensity at 288 electron volt. But if we compare the Ryugu sample, there are no sign of the aliphatic component in there. But there are 2 different data sets from the TM years. So they, Yabuta et al. Mentioned there are a lot of aliphatic rich component in the clay bound area, but aromatic rich IOM-like nanodiamonds. And recently, Chandra et al. They use a 6M like us. So there are a hint of aliphatic here. So our conclusion right now is complex diversity of carbon and nitrogen functional groups observed in Ryugu and recently found in the UK winch cone may reflect their pristine, unaltered, and uncontaminated nature. But we have to think about artifact and contamination during the SCI operations. So SCI operation, we got a debris. This is on the previously we got these samples from JAXA that we conducted all experiments as the same matter, nanosem, F5, nanosem, 6M, and so on. This is a compact carbonaceous grains like this, and the fluffy black materials like that. Looks different, but better to be cautious. And here, this is more complicated, the radiation damage during stick SEM analysis. So here, the blue is the first section of the sample. After that, the aromatic peaks increase, but aliphatic is decreased like this. So I think this is due to the irradiation of the X-ray. Even the soft X-ray cause a problem on the sample. Here, for the study, we will present. We just submitted the abstract to the coming LPSC. And here, this is a nanosims work, which is my favorite one, the bulk hydrogen and nitrogen isotope composition of fifth section by nanosims. So this is nitrogen 15, and this axis is delta D. So here, this is CM, IDPs, and CI, and so on. The red symbols indicate to the A samples, and the blue indicate C samples. And here, CI data is more likely a terrestrial number, but this is our first data. First time I saw this number, oh, this is not good. But after 3 times the measurement of the same sample, so we confirm this is the real number of the Ryugu. So here, hydrogen, nitrogen, and oxygen, and ion. These isotopes of Ryugu material display similarity to the other outer solar system materials. And these results suggest that Ryugu and the CI meteor parent asteroid could have formed in outer solar system region. Understanding fluid system in Ryugu carbonate. Of course, people may know about how important carbonates are for the fluid system in the asteroid. So if we measure oxygen and carbon isotopes together with the manganese chromium system, we have a lot of we can do a lot of interpretations, not only the age but also the fluid system. Here, if we compare with the Ryugu, some other Ryugu studies of the manganese chromium dating, so here is our data set obtained by McCain and Masa et al. At the UCLA group. It's different from Eizo Nakamura's group and Yokoyama's paper. And recently, Yokoyama et al. Mentioned bulk analysis of the manganese chromium system. This is pretty much the same of their previous article published in 2022. So here, this is our interpretation of our data set. Is the aqueous fluid responsible for the carbonate were active on Ryugu. It is, of course, early in the solar system history, within the first 1.8 million years after absolute CI age. But as I mentioned earlier, the Yokoyama et al. Is 5.2 million years. Eizo Nakamura is more likely 2.6 million years. This is some discrepancy. And also another interpretation of this data set is parent body, Ryugu parent body. So parent similar less than 20 kilometers in diameter, or of course within the large body is possible. Here, this is our latest paper, published in 2024 in Nature Astronomy. HAMP material. This is hydrated ammonium magnesium phosphorus in Ryugu. These HAMP grains may have critical contribute to the reaction pathway of organic matter toward a biochemical reaction. First time I saw this white particle in the C209 sample, I was so sure this was kind of a contamination from the Hayabusa spacecraft, but not. After we checked very carefully what kind of material, what kind of metals used in the spacecraft and the container itself. But white material is not any relationship with these materials. And the JAXA creation and micrometer, of course, as I say, found this white particle. And JAXA creation people, hey, Motoo, your creation, you have to do this. Okay, I can do that. Then we took them in the glow box, and then we conducted synchrotron XRD at Springate, and the same SEM, EDS, JAMSTEC, and Open University both. The sample was sent to the French group, and they conducted mid-infrared microspectral imaging at Soleil. So I just show SEM EDS dataset here. So I think number 6 around here, and this number 15 around here is highly related. You are able to see phosphorus, magnesium, and oxygen peaks around only this area. But of course, there are some matrix grains from Ryugu itself around here. So this is, of course, outer solar system origin beyond the most snow lines. And our interpretation of this sample is, this hump sample is in contrast to poorly solved calcium-rich phosphate. This grain favored the release of the phosphorus-rich and nitrogen-rich ionic species to enter chemical reactions. But here I have to mention this sentence here: magnesium-rich phosphate were found in Ryugu and Bennu. And our final key discovery is a terrestrial alteration for long-term storage incubation facility. This is recently published in the maps. People may know the Ogai is susceptible to terrestrial weathering. There are a significant amount of gypsum. This was rapidly formed after the fall. We conducted combined XRD, SEM, synchrotron CAT scan, XRD, and FIB-TM analysis to decide to understand the interaction of Ryugu particle with terrestrial air. These samples are available for further study. Please find them in the JAXA Hayabusa2 sample catalog. Okay. So this C80 sample, more than half year exposed to air, we are able to see a lot of calcium sulfate on the sample on the surface of the grain. But if we store in vacuum or no exposed to the air stored in the FFTC, no calcium sulfate in any samples. So this implies weathering minerals could act as an indicator for the exposure to terrestrial environment, of course. So these two is organics and volatile should be first. And then a mineral chemistry and the petrology could be done later. The storage might depend on the analytical procedure, analytical purposes in a nitrogen glow box or vacuum chamber or inert gas. Okay, based on these papers, we propose the Ryugu formation history. The outer solar system region does like this, accreted to the protolis. The Ryugu, probably less than 20 kilometers or sometimes larger. And the initial heating, aluminum-26 as a source. Then make an aqueous alteration, formation of the hydrous minerals, carbonate iron oxide, then broken of the surface, then the accretion to make Ryugu itself. Okay, the conclusion from discoveries of Ryugu sample analysis is Ryugu is a CI. based on the oxygen isotopes, abundance of major elements, and the mineral inventories. Ryugu samples are enriched with organics, and the isotopic analysis provide a clue the original provenance, most likely outer solar system of the Ryugu-derived materials. 40 minutes. Okay, questions. My point of view from the Ryugu sample, this may be solved by the Bennu sample analysis. Planet body size, smaller or larger. Homogeneous chemical composition but aqueous alteration. Age of aqueous alteration. As I mentioned earlier, so this was 1.8 or around 5 million years. This shows some discrepancy. Diversity and micrometer scale distributions of organics in primitive carbonaceous asteroid and aqueous alteration. This time, I did not mention any special space weathering stuff, but I'm pretty interested in what is the difference between Bennu and Ryugu in terms of space weathering. And the last one is trapped fluid inclusion in the pyrrhotite, containing halogens, nitrogen, sulfur, and CO2, and the silver organics. We continue this study. We continue to do this study to make better understanding evolution of organics. And more thoughts in general. You know, I did my favorite analysis is microanalysis, but in reality, we have to think more about multi-scale planetary material science. Few tens of kilometer sized bodies to few micro or nanometer scale grains. How do you compare with these two totally different types of materials? And onboard instrumental data, especially spectroscopy, this is kilometer to meter, versus laboratory analysis, any data, like a mass or Raman or FDR. FDR we can compare, I guess, on the Earth. And of course, we have to take care of the contaminations. And thirdly, and the fourth is more likely analytical instrumentation stuff. So recently, we have a lot of advanced analytical instrumentations. These provide more complex data set. How do we, at least for me, it's difficult to understand sometimes. And we have many years many years how do I say, many years experience in meteorite study. But the laboratory and age, I mean published year, bias of analysis and chemical data. We have to think about it for the to compare the previous data set and the current data set. For unlocking the full potential of planetary science and for groundbreaking discovery in the decade. This is my suggestion to the community and the curations. Work with curation, especially for the extraterrestrial materials, uncontaminated, unaltered samples. Terrestrial contamination sensitive materials like this. So analytical team is multiple expertise scientists. This is pretty important for the future sample analysis. Sample handling, especially micrometer to centimeter size, non-air exposure system. In the future, I'm hoping we have IC samples on the Earth. So we have to be prepared for that. Limited about the sample, we should do a coordinated analytical flow, utilize multi-beam techniques, including sample preparation. A systematic investigation needed organized team, not too big, but not too small. the curation is pretty important. I think they play a key role in advancing the next generation of samples return missions. Established robust collaborative networkings between curation organizations. For example, NIPL, JAXA, NASA, ESA, and maybe China as well, because they got the samples from Luna. And the leading international laboratories is critical for achieving scientific excellence and maximizing the potential of sample return endeavors. And the global creation facilities should combine annual informal or formal meeting to foster deeper collaboration and increase synergy between organizations. The world-class international laboratories should continuously improve their analytical capabilities, upgrade their instrumentations, and invest in training next-generation scientists and researchers. The multi-agency collaboration and the international partners are also important. Everything is for the groundbreaking discoveries for the coming decade, as I say. What's next? People may know the MMX and also samples of Mars. We are pretty much ready as a community. I think so. All right, thank you very much for today. I acknowledge to all of the Hayabusa2 mission operation members, of course, my team members, Open University, UCLA, and Sakley, IAS Sakley, and the fund is here. And 2 years ago, people may know we have very difficult situation under COVID, but the understanding of our family and friends and colleagues, so all are good. Thank you very much. So I'm very happy to take any questions, comments.
Motoo, thank you very much for a fantastic talk. The chat box is open, so if you've got a question, put it in the chat box now, and we'll pass it on.
Wait a second, chat box, instant chat box.
Yeah, the chat box is open. But I've got a question, Motoo, before we go.
Yes.
When they did the remote sensing of Ryugu, they had the impression that it was a, in some way, thermally heated material. How did that pan out when the actual material turned up? Why was there this big difference between the what was seen in the labs and what was seen in the remote sensing observations? Most
likely, remote sensing only the first layer of the material, so it could be a space weathering effect.
Okay. Do you have any other questions? If you want to put them in the chat box, that would be ideal.
Oh, nothing in particular.
Not yet. Everyone's a bit shy.
No.
So are you continuing to work on Hayabusa material yourself?
Not sure, but this year, JAXA Curation will announce international announcement the opportunity for the Bennu sample and the Hayabusa2 sample. I will apply that opportunity to get more samples, not only the Hayabusa, but also Bennu, and conduct the same analytical method we apply to the Hayabusa2 samples.
So Mike Zelensky is asking, do you have an idea about the dolomite age discrepancy? What's going on there?
I have no idea, in fact. Yeah, people thought about it. Maybe difference in terms of standard materials, but our group, UCLA groups, did a great job manganese chromium materials for the other organ or other materials, and their age was very consistent with previous paper. So I believe the number we received 1.8 million years, 1 million years are real.
Ming Chang has just put in the chat box. I just want to point out that the manganese chromium age discrepancy is primarily due to standards, which is obviously what you were saying. And
Okay.
Lindsay Keller, the aliphatic material in the coarse clays, is it in between the clay sheets, i.e. in the interlayer space? Are there any relationships?
Thank you, Lindsay. I think that my answer is yes, but to be sure, I would like to continue more detailed analysis with higher spatial resolution instrumentation like atom floor. So we have done several few analysis with atom floor. Then now is a data reduction phase. Once I got certain answer for that, I will present any LPSC or MESOC meeting. Please wait for a while.
Romy Hanna says, excellent talk. Any thoughts on the any thoughts on the timing of the sulfide versus carbonate formation, specifically in regards to the flinks that have been documented in some Ryugu sulfides?
Any thought on timing of the sulfide versus carbonate formation? That the flinks to have documented the same Ryugu sulfide. Good question. To be honest, I have no idea at this moment. No idea. Sorry, Hannah. New shame that described this year.
Edward Nesplua is asking, there is a new CI meteorite that was classified this year, namely the Oed Chebika 002. Do you think that this might show even closer similarities to the Ryugu material than other CI meteorites that have been studied so far? So is this new CI likely to be more similar to Ryugu than Orgay or other CIs?
I think so, but be careful with terrestrial contaminations. But in terms of analysis of mineral inventory and the major elements should work. But be careful with hydrogen and maybe oxygen should work, but the hydrogen nitrogen isotopes may affect by after their fall.
So Klaus Becker wants to thank you for your talk and sends his best regards. And Larry Nyquist, and again, great talk, Motoo. Are there any noble gas analysis planned?
Oh, we already did and published in the Nature Communications, the noble gas analysis conducted at the Open University. So please have a look.
Okay. But maybe, I'm sure there's scope for more analysis as well. I shouldn't think the Open University work is the end of the story. So that seems to be. I don't seem to have any more comments in the chat box at the moment. I think we're now just over our time, aren't we? So Christian Volmar has just said, thanks for the great talk, Motoo. Why do you perform nanosims before the TEM analysis? That's on the timing there. The SIMS beam is usually more destructive than the E-beam, I think. So he's asking you why you did it.
Yeah. Good point, Christian. So because I would like to have a hydrogen isotopes in the sample. That is the primary reason we conduct nanosims prior to the TEM.
Okay, so timing critical there, obviously. Christian seems happy with that.
Thank you.
I think we've got a few more minutes if people would like to put some more questions to Motoo. I'm sure he's very happy to answer them.
Okay.
I was wondering, one thing I would ask is how critical was the Spring 8 work in terms of your preparation? How critical was the initial imaging that you did at Spring 8 in terms of planning the rest of the analytical campaign?
It's not for the microanalysis, but also that's provide us a typical texture and the typical mineralogy after we can obtain before we made a thin section of the sample. This is very important for the bulk analytical to compare to current knowledge of any meteorite IDPs. But of course, as I said, X-ray affected organics sometimes. So our microanalytical for the samples for the microanalysis does not irradiate any X-ray. We pick small particles, not irradiate to the X-ray.
Okay. Well, so I think that's we're not getting any more questions there, and so thank you again for a wonderful talk with great insight into what has been super fantastically successful mission, which has told us so much. Thank you very much.
Thank you. Larry, I will send a paper to you. Please give me your current email address. Oh, Kevin, thank you.